Calc BC. We're still in Chapter 5, but we're now looking at a review section, going over some old material and extending into a little bit of new stuff too. You can see more on integrals day 1. We're going to be dealing with some worksheets. Take a look at our directions here. Use your calculator to evaluate. Well, we know the fundamental theorem of calculus. We've been working with the U substitution just as well. But no matter what you try to do here, for example 1, you're going to be in some trouble. In fact, we haven't even really studied at this point how to take derivatives or integrals of e to the x and so forth. We get to that later in the year. We do late transcendentals. It's in Chapter 7, actually. But let's instead just get our calculator out, and when we do that, we can very quickly press math and go down to number 9, fn int, and we'll have a lower bound of 1, upper bound of 4. We need e, so we'll go second ln, e raised to the sine x. Close your parentheses around your trig function. Come over here and type in x. And as we hit enter then, of course we get our answer of 5.164 or 5.165. I do want to point out you must be in the radian mode. We should have checked that beforehand. We have a lot of students in physics, and for those physics students, they're really jumping between degrees and radians a lot. But in calculus, we're going to always be in the radian mode. And just to let you know, 3 decimal place rounding, you may truncate, you may stop at your 3rd decimal, or you could look to the right and then round. So both answers are accepted. Okay, earlier in this unit, we talked about how the definite integral could be interpreted as net area between the graph of a function and the x-axis. Negative area would occur when your curve is below the x-axis. But what if you're asked to find the area bounded by the curve and the x-axis, or as a lot of kids like to phrase it, the total area? By the way, total area means exactly the same thing as area. Well, let's look at this graph, y equals 4 minus x squared. We have a parabola. We have a parabola that opens upside down, downward, because of a negative x squared. The 4 here will raise our curve up 4 steps up. If we wanted to find our x-intercepts, we'd let y equals 0. We could solve very quickly. I think kids can more or less know, even solving in their heads, that you'd have a 2 and a negative 2. Well, as you're looking here, the big question is, what's the area bounded by the curve and the x-axis? Well, part of this curve is above the x-axis. We'd expect to get positive area here in yellow. But the other part of the curve is going to be below the x-axis. So we'd expect to get negative area here. And really what we need to do is to be aware of that fact, and we're going to very quickly address where we'd have positive area. That would be the integral between 0 and 2 of 4 minus x squared dx. And where we expect to get negative area. The negative area, of course, would go from 2 to 3. Notice what I'm not doing. I'm not just integrating between 0 and 3. This right here would be net area. This would allow the positive and the negative areas to cancel each other, and we don't want that to happen. We want to keep track of both the positive and the negative area. Now, of course, this problem in particular we can do by hand, but for the sake of time, let's very quickly, notice what I did. I hit math and I hit the up arrow to speed this up a little bit. You could most definitely get this worked out very quickly with the calculator. We get a fraction, 5.3 repeating, or 5 1/3. I hope you know that 5 1/3 is 16/3. That's a positive 16/3 at that. By looking at this other section, we can say, well, my goodness, what if we did a second enter again, and this time we said, look, go from 2 up to 3. And when we get that, of course, we get something negative 2 1/3, which is negative 7/3. So we have area above the curve, area below the curve. But if I were asked to find the total area, we convert negative area to positive area. We're going to make this positive. Keep positive area positive, convert negative areas to positives, and your final answer would be 23/3. Okay, by the way, if that seems familiar, we have done that before. We're just reviewing. Let's take a look at an old problem, a problem that you very well saw in elementary school. In elementary school, I hope you were first told about the distance equals rate times time formula. One of the most famous formulas you're going to do in math and physics. You have a constant speed of 75 miles per hour. You're going to be traveling for 2 hours. And you very simply multiply. You can see your units cancel. 2 times 75, of course, is 150. So you could say, well, that's 150 miles traveled. Usually kids look at that and say, okay, no big deal. I guess the one thing I do want to raise up to you is that you could look at this in terms of area. And you could say, look, between 0 and 2 hours, what if your speed was consistently at 75? You could find this area right here. The base of this rectangle is a 2. The height is 75. 2 times 75, of course, is exactly what we just did. Why am I bringing this up? Well, if we're talking about area having real-life applications, and it certainly does, that means integrals can be used in real-life applications as well. Of course, we dealt with speed in our last problem, but let's be aware that velocity is going to get thrown in just as well. And velocity, guys, my goodness, as we're looking at this, velocity is really going to be more of a physics application. We're going to see that way more than we would with speed. When velocity is positive, your object travels to the right. When your velocity is negative, you travel to the left. So if we were to actually deal with area above the curve is distance traveled to the right. By way of comparison, when your velocity is under the curve, and you might have negative 10 miles per hour, and if you were multiplying by hours, well, you'd get your distance that you traveled to the left. So here's what we need to be aware of. If we're integrating from a to b of v of t dt, this is displacement. This is where you have net area. And your positive area could cancel with your negative area. And whatever answer you have, whether it's positive or negative, that would indicate that you're traveling more to the right or more towards the left at the end. But look, from the fundamental theorem of calculus, we talked about this before. If we took an antiderivative, this would be s of b minus s of a. It's your change in position. Wow. And that's so very, very, very important. That's really what we're seeing right here from the fundamental theorem. Whatever rate you are integrating, as you integrate that, this is your change in f. It's your change in f of x on the interval from a to b. Wow, change. Here we go again. Very likely you were studying this whole unit. Maybe you recall at the start of this class, I said calculus, if you could describe it in a word, is a study of change. Wow, even right here in integration, we're seeing that. But listen, just want to throw this out here too. If we integrate net area, we're dealing with change in position. You might think, how in the world do we get distance? Distance traveled. Of course, you don't want to have negative area. A way to deal with that is to integrate the absolute value of velocity. Put absolute value around velocity and any negative velocity curve becomes a positive. Everything gets flipped over to the being above the x-axis. So that's how you can go quickly to find distance. Well, let's take a look at one last problem right here. And it says, we very well might be seeing this as a future test question. We're going to look at this interval from 0 to 5. We're given that s of 0 equals 9. Ooh, is that important? And we'd like to know the position of your particle at t equals 5 seconds. Tell you what, we're on an interval from 0 to 5. I'm going to integrate velocity. I'm going to just type that in real quickly. And we'll see what we get. You know, as I'm just integrating here, I'm going to get displacement. I'm going to get my change in position. So let's see what happens here. I'd like to know how this works out. I'm going to type in math. Come up here to fn int. We'll go 0 up to 5. I'll have x squared minus, let's get a fraction, second, or alpha y equals, and we'll get 8 over parentheses x plus 1, square that. And guys, as you work this out, it's only going to take you a moment. That's going to be 35. What did you just find? You just found the change in position. That's not the total distance traveled. The change in position is 35. So what did we start with? Well, you're told s of 0 is equal to 9. So we're starting at t equals 0 at 9. And then we have this change. It's positive. By the way, this number, the change, could be negative. 9 plus 35 is 44. So where are we at 5 seconds? S of 5 would be 44. Displacement, when you just integrate velocity straightforward like that, that's the change in your position. Don't forget, you have to add back to what you started with. For B, total distance traveled. Tell you what, guys, with a calculator, if you have a calculator, this becomes one of the easiest problems that you could deal with. Look at this. I'm going to integrate with the absolute value. You can do that. Look at this. Math, I'm going to up arrow. Come right here. I'm going to say go from 0 all the way up to 5. But now I need absolute value. I'll hit math. I'll go to number in ABS. And then I'll type out exactly what I had. What I'm really doing here, guys, what I'm really doing is I'm guaranteeing that my velocity curve is never negative. I'm guaranteeing that my velocity curve could be 0 at worst, but otherwise it's positive. And it only takes you a moment to get this thing typed in. Look, you don't have to find out where your curve crosses